was mentioned, I am Brian Gottfried, and this project was advised and sort of directed by Diane Pozefsky. If you were here last year, you probably saw Ian Kim present on something really similar to this. This is a continuation of his project. A lot of this is owed to him. We kind of took the test prototype that he built and built it out to see what would happen to scale. So really what this is about big data and scaling. And we're going to see whether NoSQL databases really scale like relational databases do, or if they scale better than relational databases. So an overview of the Chemotext problem. It's built on Swanson's ABC paradigm. This is essentially a theory that states that if you have some chemical and some disease and you think there might be a connection between them, but you don't know what it is, you can determine if there's a connection or not by looking at several intermediate terms that may connect them. Usually those terms end up being proteins, so the way that it's broken down in the Chemotext system is you've got chemicals and proteins and diseases, and you're looking for connections between them. To find those connections, you're looking at Pubmed. That's the basis for pretty much the entire database. Pubmed's it's like a medical journal citation database, essentially. It's got about 22 million articles, not the full text of them, usually just the citations. And then as well, it also has a dictionary of 28,000 mesh terms. And those mesh terms are they're the qualified and established terms by the National Library of Medicine for what you should use to reference things. And we're going to see that those aren't always followed, and that's kind of part of the problem with this and something we had to deal with. So this is a big data problem, like I said. When I was dealing with the input files, each one of them is greater than a gigabyte, and it's pure text. You cannot open that in a text editor, like on Vim, or just pull up Notepad. If you need to make a change to the header, it will crash. You need a specialized tool for it. You got to work around with it a little bit. A lot of times it's easier just to write a script to deal with it instead. Processing is really slow. Part of our process, some process runs in like 8 to 10 minutes. Another part takes about 6 hours, and another one takes about 24 hours to run. So if you make an error and you don't realize it until half an hour or like halfway into it, you got to start it all over, and you just got to wait and deal with it. So it causes its own problems, and you got to be patient, and you have to be creative with it. And hardware definitely helps. We ended up moving to a compute cluster on ITS for a portion of the processing, just because we weren't going to see results for several days at a time otherwise, or at all. So going back to the NoSQL portion of this, if you know anything about databases, the dominant model for databases for the last 30 years has been relational databases. And those are databases that use SQL or structured query language, and they're built on a model of tables with rows inside those tables. This has worked really well for most businesses and most use cases. But in the last 10 years or so, as data's gotten bigger, and as we've gotten data that's more complex and harder to kind of quantify into a single table or a few tables, NoSQL has kind of grown out as an alternative database format. There's 4 main types. There's key value stores, column stores, document databases, and graph databases. I'm only going to talk about graph databases. I can talk about the other ones another time if you'd like to, but graph databases are what are relevant for the moment. And they're essentially built on graph theory. They're an outgrowth of the network databases that started back in the 1960s, if you know anything about database history. But the data model for them essentially is there's nodes and relationships. And nodes are anything in the database that's an object, and then a relationship is just a relationship between nodes. It's relatively simple, and it makes things pretty straightforward that way. So this is like an example of Neo4j on the left. It's a very simple one. It's a movie database where you've got movies and actors and directors and the relationships between them. And it's pretty easy to model. The nodes are all those square-shaped things. You've got labels for the nodes, which is a recent addition to Neo4j, and it's very helpful. And then the relationships are the lines between them. On the right, that's the relational database equivalent of this database, really roughly. It's not as pretty, it's not as intuitive, and a lot of stuff like maintaining consistency across those labels isn't really feasible. It's doable, but it requires a lot of extra logic, and it's not fun to deal with. So this is the kind of problem that Neo4j excels at. We're going to see that Chemotext works that same way. This is the ABC paradigm as represented in a relational database and in Neo4j. You're looking at a join of 2 big join tables and then 2 separate tables aside from that for 3 total joins in order to represent that relationship. In Neo4j, it's just 2 relationships as a hop, and all those nodes are directly connected to each other. You're not looking through the entire set of nodes that way. So we're going to see this has really big performance implications. So this is the Chemotext relational model. It's kind of similar. It's a little bigger. You've got 4 tables for just referencing stuff, the chemicals, diseases, proteins, and articles. And then you have 3 join tables, this disart, chemart, and protart. And those represent the relationships between an article that mentions some sort of mesh term. On the right, that is the query syntax for it. It's ugly, it's messy, and it's really, really slow. You're looking at 3 joins, and these aren't small tables. So I believe that Ian mentioned during his presentation some of these queries can take up to 15 minutes to run on this system. So it wasn't really feasible. And these are the main issues. The first one is the table size. These numbers are almost conservative, and even so, if you're looking at a joining of 500,000 to 11 million, I forget the exact calculation for a join off the top of my head, but it's essentially a cross product. So it's not going to be a pretty number. It's going to be really, really big, and that was borne out in this. That even performing on a decent database on a system with a decent amount of memory and good CPUs, it just was not coming through quickly, and that's because the RAM can't hold that large of a join table. And then you're looking at multiple joins as well, which only compounds the problem, and that makes it slow. So this was the model that Ian came up with in response to that. It's a Neo4j model. It's very, very simple. There's only two types of nodes. There's a mesh term and an article. You want to differentiate between the types that way, and then there's a relationship between them, and that's about it. The query syntax is on the right next to it. It's a lot simpler. What this essentially says is you start with some node in this index, and you find it based on the lowercase name aspirin. The index is on that attribute LC name. And then you match for every article that mentions that chemical and every other term that's mentioned by those articles. And then you are only looking for disk condition types, and then you return the names of those other ones. So that's kind of how the syntax in Neo4j works. We'll see there's been some changes in the recent updates recently. The new syntax is a little different. One of the big things, though, is that when Ian did his implementation, he did it on a smaller subset of the data. He was working with just the articles from 2002. So the stats, the number of terms and articles combined was about 450,000, and the number of relationships was 5 million. In this full implementation, we have 11 million terms and articles and 94 million relationships. So that's a pretty big step up, and we weren't really sure whether it was going to scale or not. We didn't know what was going to happen when we got to something that large. Just as a little precursor, we see that the baseline query time is definitely different, and it did fall behind a little bit, but not on the same order of magnitude. We found the average query time was really roughly the same and was still sub-second, which is really the important thing we were looking for. So this is the first update we made, is that when we changed to Neo4j 2.0, they changed how they did their labeling. And the really nice thing about it is that all the labeling and the indexing is automatic now. The indexing back in 1.6, which is what was used originally, you can only maintain one index automatically. Everything else you had to manually maintain, which is a nightmare to try and deal with, especially on data this size. So we made the change to that, and all that did was that changed the query syntax a little bit. You can see down here, the only thing that really changed is this. And that's pretty much the same, and the attributes of the nodes have changed a little bit. Nothing huge there. And then the second change we made was we added in this synonym relationship modeled by this is-master term relationship. Essentially, the issue is, while the mesh terms are supposed to be the terms you always use in order to reference a chemical or disease or a protein, people don't do that. There's changes to the names, there's slight misspellings and that sort of thing, and those are all over the articles. So rather than try and go through all the articles and fix them, they just have in the mesh dictionary a set of related terms that are synonyms for those things. We didn't want there to be a lot of duplicate relationships between like a mesh term itself, the canonical term as you would call it, the master term, and one of the synonyms. So instead we modeled it where we connected every synonym to the master term and then only connected the master terms to the articles to trim it down a lot. So that changed the query syntax a little bit here, and we actually looked at two ways of doing that to kind of check out the performance aspects of this. We tried doing it in just Neo4j with that new relationship. We also tried bringing SQL back into the picture. We essentially built a MySQL database that had one table in it, a table of synonyms. It's a single table thing that just 2 columns. It's got the synonym and then the master term for it. And we thought, why don't we test and see how each one performs and see the performance aspects of them, because this is what SQL is great for, is an index table, only a single retrieval, you're not doing any sort of joins. The results weren't really impressive. We didn't see any sort of difference between the two of them. The Neo4j plus SQL is slightly slower in the meantime. That could be any sort of factor. Essentially, they're roughly equivalent in their performance. We decided to stick with the native Neo4j because it meant you're dealing with one less system. That means you can free up more system RAM for Neo4j. It's less maintenance, and there's less connection lag as well from that. And then the other big thing we tried to do besides that was we were looking at caching performance. And we wanted to see, since we had I think it was approximately 11 million articles and 300,000 combined synonyms and mesh terms, most of what you're looking for is going to be repeated. You've got a lot of articles in there, but not very many mesh terms. So rather than searching through all of the nodes in the database, we thought, why not try and cache them and just request them back that way and save ourselves some time. We looked at 2 main ways to do that, either using Memcached or Elasticsearch. Memcached is it's a separate caching utility that is, again, kind of considered a NoSQL database. And it was developed, I think, starting early 2000. It just works like a caching system, but it's a separate bit of software, and you can establish across a bunch of servers and maintain the same virtual cache that way. It's a nice little tool. We found it didn't really work for what we were looking for. Elasticsearch is kind of a similar concept. Instead, it's mainly focused on full-text indexing, so it's great for indexing documents. You can use it for indexing database objects as well. We found that in either case it wasn't terribly useful. We did the performance testing with Memcached, and again, we found that it was actually slower in both cases. Turns out the reality is that Neo4j is a really good caching system, and the big deal with this database is we're trying to match those relationships. And if you want to duplicate those in Memcache, you're going to have to grab a huge portion of the database to do it. It's not efficient to do that anyway, and then also Memcache isn't built for that sort of thing. This is what Neo4j is built for, is dealing with those relationship connections. So we found that your best option in most cases is to go with a native Neo4j implementation. And this is just a summation table here.